Okay, let's jump right in. Today we're doing a deep dive into the massive computational hurdles of AI video generation.
And we're focusing on a new framework, SemanticGen, that's taking a really interesting shortcut. It's
Mhm.
prioritizing meaning over just, you know, millions of pixels.
Right. So our mission here is to unpack how that conceptual shift is supposed to solve the two biggest headaches in this space: slow speeds and keeping videos coherent.
Exactly. It's all about quality and efficiency.
So let's set the stage. Why have current AI systems been running into such a wall here?
Well, the standard approach operates in what's called the VAE latent space. You
Oh.
can think of it as this incredibly detailed, pixel-heavy canvas.
Okay, so it's modeling every tiny detail from the get-go.
Every single one. And to get high quality, you need a brutal computational budget. We're talking hundreds of thousands of GPU hours.
Russ, just for training.
That's an enormous amount of resources, and a
Mhm.
lot of it is spent modeling noise and detail that
Yeah.
doesn't fundamentally change the scene.
And I'm guessing that inefficiency just completely breaks when you try to scale it up to, say, a 1-minute video.
It does. The source material notes that 60 seconds of video becomes over 500,000 tokens.
Hmm.
The models that can handle that, these full attention models, they just aren't practical at that scale.
And that's where we get that weird temporal drift, right? A character's shirt suddenly changing color or the background flickering.
Precisely. The model basically runs out of its attention span because the data is just too heavy, too redundant.
So if the pixel-heavy VAE space is the problem, what's SemanticGen's lightweight alternative?
The core insight is, well, it's recognizing that video is immensely redundant. A car driving down a street is mostly the same car, same street, same motion.
So you don't need to reinvent the wheel for every single frame.
You don't. So they came up with a two-stage process. First, you perform what they call global planning. It's like building a house. You start with the blueprint, not the paint color.
Okay, so let's unpack that blueprint analogy. How does it work?
So the first stage is the planner. A diffusion model generates these really compact semantic video features. That's the blueprint. It locks down the high-level structure, the motion.
And then a second stage comes in and what, paints the walls?
Exactly. It takes that blueprint, and another diffusion model generates the actual video latents, adding all the high-frequency visual details, the texture, the exact shadows.
Well, here's the part that really stood out to me in the sources: the compression step. They take those semantic features and radically shrink them.
Oh, it's a huge reduction. We're talking about going from, say, a 2048 dimension down to 64, or even as small as 8.
Wait, down to 8? That seems extreme. How are they so sure they haven't just thrown out all the important information?
That's the key, isn't it? The confidence comes from what they keep versus what they discard. The compact blueprint is designed to only encode the high-level stuff.
Things like structure and the motion patterns, the dynamics of the scene.
Right. It keeps the blueprint. The bee is hovering, the car is turning. But it gets rid of ephemeral things like the precise fuzzy texture on a flower petal.
And that low-level stuff is just handled later by the second stage.
Exactly. And decoupling it like that is what makes the whole process converge so much faster.
So this focus on the compact blueprint is what finally solves that drift problem we see in longer videos.
That's the idea. For a video up to a minute long, SemanticGen can run its full attention model only on that tiny compressed semantic space.
So it's only tracking the big picture.
The big picture, the major narrative elements. And because of that, it maintains long-term consistency. The characters and scenes stay stable.
And the results really do seem to bear this out. We're seeing complex actions like a car driving through a neon city or multi-shot conversations that just hold together.
So when you boil it all down, the value proposition is pretty clear. SemanticGen means faster training and much better coherence for long videos. It's a shift to modeling ideas, not just data.
It really is a brilliant conceptual shortcut, but it does rely on these pre-trained visual encoders that sample video frames at a pretty low rate. The source said 1.6 frames per second. And that raises a really interesting question for you, the listener, to think about.
Which is?
If focusing on this high-level meaning solves the coherence problem, what essential high-frequency details might be getting lost in the process?
Right, like a tiny instantaneous flicker of lightning or a brief flash of motion in someone's eyes. If you're only sampling so few frames to get the meaning, are those details lost forever?
Something for the next generation of AI development to explore.